Inside an evacuated drop shaft, a ball waits 80 meters above the capture floor. The gates below do not measure speed. Each one records where the ball is and when it passes. A release. A moment later, the record is complete. Positions, times, a bright trail through the dark. But one question is still missing from the data. At exactly 2 seconds, not before, not after, how fast was the ball moving? Let downward be positive and call the downward displacement S. The gates report 0 meters at 0 seconds, 5 at 1, 20 at 2, 45 at 3, and 80 at 4. Move those records onto a time graph. A smooth curve through them is described by S of t equals 5t squared. That formula is only a compact model of this ideal fall. It has not yet answered how fast now. Over a stretch of time, speed is easy to estimate. From 2 seconds to 3, the ball moves from 20 meters to 45. That is a change of 25 meters during 1 second. An average velocity of 25 meters per second. On the graph, the same calculation has a shape. Join the two records. The line rises by 25 while it runs by 1. Its slope is the same ratio, change in position divided by change in time. This secant answers how fast over this interval. Our question asks for 1 instant. So make the interval less blurry. Keep the first point at 2 seconds and bring the second point closer. At 2.5 seconds, the average is 22.5 meters per second. At 2.1, it is 20.5. At 2.02, it is 20.1. The time gap is shrinking. The secant is rotating toward a stable direction. We never replace the time gap with 0. That would ask us to divide 0 by 0. Instead, we ask which value these averages approach as the second point closes in. Approach from the other side, and it agrees. The averages approach 20 meters per second. The moving secant settles into the tangent at 2 seconds. Its slope is the ball's velocity now. That instantaneous rate of change has a name, the derivative. At 2 seconds, the derivative of position is 20 meters per second. Written as a limit, it says, compare nearby positions, divide by their time gap, and ask what the ratio approaches. Because we chose downward as positive, the velocity here is positive 20, and the speed is its magnitude, 20. Now slide the tangent along the whole position curve. Its slope starts at 0, then becomes 10, 20, 30, and 40. Those slope values form a new function, velocity. Position told us where the ball was. The derivative extracted how fast it changed. Now hide position and keep only velocity. Can these changing speeds rebuild how far the ball fell? 1 speed times 4 seconds cannot work because the speed never stays one value. We need to collect many small changes. At each time, the height of this gold line gives downward velocity. It begins at 0 and increases by 10 meters per second every second. At 2 seconds, it is 20. At 4 seconds, it is 40. The line is described by v of t equals 10t. But the detector asks for meters, not meters per second. From 0 to 4 seconds, how can a graph of changing velocity produce a total displacement? Take one short time slice with width delta t. Across a short slice, the velocity changes only a little, so its added displacement is approximately velocity times that time width. Meters per second times seconds leaves meters. Now cover the 4 seconds with 4 wide bookkeeping slices. Using the velocity at each left edge gives 60 meters, clearly short of the real total. Make 10 thinner slices, 72 meters. Make 40, 78. The staircase hugs the line more closely, and the missing gaps shrink. Keep refining the same idea, and the strips merge into the exact accumulated change, 80 meters. The rectangles never claim the ball moves in jumps. They are temporary accounting pieces for a continuously changing velocity. Exact accumulated change has a name, the integral. From 0 to 4 seconds, the integral of velocity with respect to time is 80 meters. The lower and upper numbers mark where accumulation starts and stops. The function v gives each strip's height. The dt remembers the time-width idea. We have not used an antiderivative rule. We have built what the symbol means. If velocity crossed below 0, that part would subtract from displacement. In this fall, downward velocity stays positive. Now put the two views together. Start with position. At every time its tangent slope gives velocity, differentiation extracts change now. Start with velocity. Accumulate its signed area from the beginning, and it gives position change. Integration collects change altogether. At 2 seconds, the position slope is 20 meters per second, while the area under velocity from 0 to 2 is 20 meters, matching the position change. At 4 seconds, the accumulated area is 80 meters, matching the fall. For this smooth motion, and more generally under suitable conditions, differentiation and integration undo each other's work. That is the intuitive promise behind the fundamental theorem of calculus. Today we see the map, not the proof. Questions about tangents, motion, and areas had occupied mathematicians for generations. In the 1660s, Newton developed his method of fluxions, treating quantities as flowing with time and connecting their rates to motion, tangents, and inverse problems involving quadratures, areas. Leibniz developed calculus independently and published a different formulation. His d and integral notation became the standard language we still use. Calculus was not suddenly caused by one falling apple. It grew from sustained work on exactly this pair of needs: change at an instant and change accumulated across an interval. Calculus begins with two questions. How fast now? Follow nearby change toward a tangent, derivative. How far altogether? Gather changing rates across time, integral. One extracts a rate, the other rebuilds change. Next, we will learn to calculate both. For now, remember the map: slope locally, accumulation globally.